Hello, my dear students. I hope you're fine. Let me take one important theorem related to the invertible transformation. The regular. The statement of the theorem is like this: if V is a finite dimensional vector space over F, then T belongs to A of V. A of V means subalgebra that you know is regular is regular if and only if T maps V onto V. And you know the definition of onto property. Before I take the theorem, let me recall the definition of ontoness. The onto definition. F is a function from A to B. For each B belongs to B, there exists an element A belongs to A such that F of A equal to B. That you know. This word is very important. Before you prove the theorem, recall the definition of the ontoness. Okay, since T is regular, if it is regular, what will happen? If T is regular, we know so many results. According to one of the result, there exists T inverse in subalgebra, that is A of V, such that the product of T dot T inverse is equal to T inverse dot T equal to the identity element, that is I. Let me continue the proof of the theorem. Take an element V is a vector, the element belongs to finite dimensional vector space, that is V. This can be written as V belongs to V can be written as V equal to Vi. That means finite dimensional vector space is replaced by the element of this, that is Vi. Again, I means either you may take T dot T inverse or T inverse dot Ta. Here I have taken T inverse dot T. I is replaced by T inverse dot T. Grouping, we get this. Again, I'll replace this bracket by an element W, T as it is. Taking T to left hand side, Vt inverse is equal to what? W. And this belongs to what? The finite dimensional vector space V. What it indicates? V belongs to Vt. That means if V belongs to V, then the same element belongs to Vt. What Vt stands for? Vt stands for the range space of a linear transformation. Therefore, V is subset of Vt, and we define the Vt by this definition, that is range space of a linear transformation. We know that the range space of a linear transformation, that is Vt, is always subspace of V. And one more condition, Vt means range space of T is equal to finite dimensional vector space only when the mapping is onto. Keeping this result in mind, let me continue. Since V is a subset of Vt, but Vt is always subset of V, therefore V equal to Vt. V equal to Vt means the T is onto. Let me prove converse part. I'll prove the converse part by contradiction method. If possible, T is not regular. T is not regular means T is not onto. Okay. If T is not regular is same as saying singular. If it is singular, again by standard result, there exists an element V1 provided that element is non-zero in a finite dimensional vector space V such that image of V1 under T, that is V1T, is equal to what? 0. We write this statement, I mean this result, only when it is what? Singular. If it is not regular, that means it is not onto. If it is not regular, means it is singular. If it is singular, this result holds good. Let me continue. If the dimension of a finite dimensional vector space, if the dimension of a vector space V is M, say that means we have taken n number of elements. The set containing a vector Vi can be enlarged. That means extended. Yavak Sadhya, this is possible only when the vectors forms a basis. Since we see the word dimension, that means it is a base. It is a basis of a vector space. Since it is a basis, therefore the vectors are linearly independent. The vectors are linearly independent. It can be extended. Okay. The set containing the vector Vi can be extended or can be enlarged to what? The set containing n vectors. What it forms? Since we see the word dimension, therefore it forms a basis. Let me continue the proof of the theorem. Image of V1 under T is equal to 0 and I'll denote by W1. And image of V2 under T, that is V22 equal to W. In general, V and T equal to Wn. What we claim that here we claim that the set containing n vectors span a range space of a linear transformation, that is Vt. Spanning means linear combination. We know that L of S is equal to V. This we have studied in UG. L of S is equal to V means for each vector, I mean if the vector beta belongs to V, then beta can be expressed as linear combination of S. That means L of S is equal to V. Keeping this basic idea in mind, here we see beta belongs to V. Now I will take W belongs to range space of T, that is Vt. Now this can be written as W belongs to Vt can be written as W equal to what? Vt, where V is an element of V. Again, W is equal to the linear combination of vectors like V1, V2, Vn. Since W equal to taking T inside and the scalar outside, we write like this. Since V1T equal to 0, here we have, since V1T equal to 0, that means we have to ignore the first element. If we ignore the first element, W can be expressed as lambda 2 W2 plus lambda 3 W3 up to what? Wn, lambda n Wn. What it shows? This shows dimension of range space of T, that is dimension of Vt, is less than or equal to n minus 1 because one element, one vector is less here, and n minus 1 is always less than or equal to n. What is n? N means dimension of vector space, and this is, since n minus 1 is less than n and n means dimension of V, what it shows? Dimension of range space of T, that is Vt, is less than dimension of V, which is contradiction. Since it is contradiction, that means it is not onto. Not onto means not regular. Okay, this completes the proof of the beautiful lemma, I mean the theorem. That means that is that is if V is a finite dimensional vector space over F, then T belongs to F is regular only when T maps V onto V. That means here we made use of the onto property, singular, the result related to the singularity as well as regular. Okay, I hope you got it. So in next hour, I'll take the eigenvalues and eigenvectors of a linear transformation. Okay, thank you. Have a nice evening.